Hey everybody, today we are going to talk about the Rolle's theorem and the mean value theorem. And I'm going to do things a little bit differently. I'm going to be pasting in my typed up notes, so it's going to be a little bit neater, but it'll look a little different. So let's see how this works. So first off, we have the Rolle's theorem. And essentially what we says, if we have some function, as long as it's continuous on a closed interval, so if from a to b, as long as f of a is equal to f of b, right? Then what that guarantees us is there has to be some point C somewhere in here. It turns out it's going to be about here, where the slope of the tangent line here, or the derivative, is equal to 0. There's no way around that. If you start at the point a comma f of a and you end at the point b comma f of a, which is the same y coordinate, you must level off at some point on this smooth curve. So for example, let's prove that x to the third plus x minus 1 equals 0 has exactly one real root. So what we're gonna say is, first off, we can use the intermediate value theorem. We know that this is continuous. F of x equals x to the third plus x minus 1 is continuous, and it's differentiable. Okay, so we know that f of 0 is negative 1, and f of 1 is equal to 1. So we know by the intermediate value theorem, there exists some c in the range 0 to 1. Actually, it's in the open interval from 0 to 1, such that f of c equals 0. Like, we know that there has to be at least some root, because this thing goes from below the x-axis to above the x-axis. Now, the question then is there any other real root? Is it possible there's any other real root? Remember, polynomials, if they have a complex root, they come in pairs. So this thing, if it has one more real root, then it has three real roots. Okay. Okay. So let's suppose f has two more real roots, a and b. Okay, so f of a equals 0, and that's equal to f of b. And because this thing is differentiable, we know that there has to be some point in the range a to b where the derivative is 0. Well, what is the derivative? F prime of x is 3x squared plus 1. Okay, so this is, if we set 3x squared plus 1 equal to 0, what we get is a problem, right? 3x squared plus 1 is never equal to 0. Never equal to 0. Why? Because you have 3 times x squared plus 1. That's never 0, because 3x squared is no smaller than 0, and you add 1 to it. That's not true. So this is a contradiction. So a and b cannot, in fact, even a can't exist, because if there was an a, some other root besides the one that we know exists, then there can't be two roots of this, because if there were two roots, then the derivative would be 0 somewhere between them. And the derivative is never 0. So since the derivative is never 0, there cannot be two real roots. Okay, here we go. Now we get to the mean value theorem. This is it's a generalization of Rolle's theorem. So if f is some function, it satisfies the following two hypotheses. It has to be continuous on the closed interval from a to b. So here's a, and here's b. And here's what this function might look like. and it has to be differentiable on the open interval. So as long as it's smooth and doesn't have any pointy parts, but we don't need a and b to f of a equal to a of b. Then the mean value theorem says there has to be some value between a and b such that the derivative at c is equal to the average rate of change. So the average rate of change would be the slope of the secant line connecting a and b, and there's going to be some point along here. There's guaranteed to be some point between a and b where the slope of the tangent line there is equal to the slope of the secant line. That's the mean value theorem. It's guaranteed to be the case. As long as it's continuous and differentiable, this is always going to be the case. Okay, let's consider this function f of x is x to the third minus x on the interval from 0 to 2. So let's just, f of 0 is 0, okay. F of 2 is 2 to the third minus 2. That's 8 minus 2. That's a 6. Okay, so the average rate of change, we want to find some c on the interval from 0 to 2 such that f prime of c is equal to the average rate of change, which is going to be, there's a change in the height of going from, so 6 minus 0 over 2 minus 0. So that's a height of 3. So the derivative, we can find that, f prime of x, 3x squared minus 1, and we're going to set 3x squared minus 1 equal to 3 and try to figure out what this might be. It turns out we can, if we subtract, well, let's see, we can add the 1 to both sides. Well, let's see. We have x squared equals 4/3, right? So x is going to be plus or minus 2 over root 3. And it turns out that 2 over root 3 is between 2 and 0. So that's going to be our c. C is going to be 2 over root 3. So there is this point between 0 and 2 where the derivative at that point is exactly equal to 3. That's the mean value theorem. Okay, so if a car is traveling at 180 kilometers, travels 180 kilometers in 2 hours, we know for a fact that the speedometer must have been 90 kilometers per hour at least once. Why? Well, let's let f of x be the, actually let's let f of t is the distance traveled after t, let's say t hours. So we know that f of 0 is equal to 0, f of 2 is equal to 180, right? And so that means by the mean value theorem, there must exist some c in the interval from 0 to 2 such that f prime at c is equal to the average rate of change. That's 180 minus 0 over 2 minus 0. Well, that's exactly equal to 90. So that means there has to be some point at some time between 0 hours and 2 hours, the rate of change of distance, i.e. the speed, must have been, the speed at time c is exactly 90 kilometers per hour. That must exist by the mean value theorem. All right, let's suppose, take another example. Suppose that f of 0 is negative 3 and f prime of x is less than or equal to 5 for all values of x. The slope of this curve never gets bigger than 5. So how large could f of 2 possibly be? Well, what that means is that there can't be that we can say by the mean value theorem, the derivative at any point c is less than or equal to 5, and so for the average rate of change between 0 and 2, so there's going to be some point where the average rate of change, which would be f of 2 minus -3 over the range from 2 to 0, this has to be less than or equal to 5 for the slope at the value at 2 can't exceed, there's a certain value it can't exceed, because if it does, then there would be some point where the slope would be greater than 5, right? So let's figure that out. So f of 2, that's going to be f of 2 plus 3 over 2. Actually, what I'm going to do is multiply both sides by 2, would give me a 10 over here. F of 2 has to be less than or equal to 7, right? So what this means, like if for example f of 2 is equal to 7.1, okay, then that means there exists a c such that f prime at c is going to be 7.1 minus -3 over 2, and this is greater than 5, but this cannot be. So that's the idea. Like, we can use the mean value theorem to kind of put limits on the possible values of the function. So we get a theorem that comes out of this that if the derivative f prime of x is equal to 0 for all x in an interval, then the function must be constant on this interval. And so let's talk about, let's actually do the proof of this thing. Justify that we know that f of a has to be the same as f of b, because if not, then there exists, well then f of b minus f of a over b minus a is not equal to 0, so there exists some c in the interval a to b such that f prime of c is not equal to 0, right? But we know that the derivative is equal to 0 for all values in this interval, so this cannot be. Okay, so now let's suppose that there exists some c in the interval from a to b such that f of c is not equal to f of a. Right? That, in other words, suppose that the function isn't constant. There's some point between a and b where the function value isn't the same as the endpoints. But that means then f of c minus f of a over c minus a is not equal to 0, so there exists some d within the interval from a to c such that the derivative at d is not equal to 0. But this is a contradiction. Thus, f is constant on a to b. It has to be. So there's a corollary that comes out of that, which is that if the derivatives of two functions are equal to each other for all x on an interval from a to b, then the difference of the two functions must be constant on that interval. So the functions must differ but only by a constant. For if they don't differ by a constant, then you would have some contradiction that their derivatives must not be equal to each other at some point along the interval. So the mean value theorem has a bunch of different applications. Really, we're going to just see lots of different ways to apply this stuff in class. But this is the mean value theorem and Rolle's theorem. Rolle's theorem is the special case. Mean value theorem is just a little more general. And yeah, we'll see how we can look at applications of this in class. All right, bye.